by the early 1900s, we had developed these two fundamental ideas of matter at the subatomic level. One is that energy is quantized. The energy only comes in discrete packets. That means that not all energy values are valid, that there's a minimum value that it can be associated with it. And it has to come in a multiple of those values. Again, something similar we see, like when we're balancing equations. Sometimes you can only have multiples of atoms. Same idea here, except related towards energy. Additionally, within the atom, the electrons exist in discrete energy levels within the atom. So for the simplest atom, hydrogen, the energy levels are arranged in these sort of orbits around the atom. This is Bohr's model for the atom. The hydrogen atom has the nucleus, and then around this, the electron can exist. Normally it exists in this lowest energy state, the ground state, the lowest energy level. But when we excite the electron, add energy, if we add the right levels of energy, we can get the electron to jump from one energy state to the next. This is what we see when we excite the atom. If you pass an arc current through the atom, through a gas containing, it emits, the atoms become excited, and then they emit energy appropriate to the energy levels that we observe. So what we're seeing when we excite the atom we've excited the atom, we've added energy, we see the electrons hopping between various energy levels, this quantum leap. And when they leap, when they hop down, they emit light, h nu, of a particular energy. And we can predict that using this equation, so Bohr's equation, that involves this Rydberg constant, this constant associated with the hydrogen atom. This only works for the hydrogen atom. When you start to make atoms more complex, the energy levels start to become strange. We don't see these discrete energy levels. And we'll talk about that in a second. So let's apply this. Let's predict some information. So let's calculate the wavelength in nanometers of a photon emitted from a hydrogen atom when an electron drops from principal quantum energy level, principal quantum number n equal to 5 to n equal to 3. So we have an atom with its arrangement of orbitals. N is equal to 1. Again, there's no 0. N is equal to 2. N is equal to 3. N is equal to 4. And what you see is that as you increase the energy levels, the orbits get more and more compressed. The energy that associated with them gets more and more compressed, so that the difference between the 5 and 6 state is less than the difference between the 3 and 4. This is a common feature in all atoms. The atoms get more and more compressed. And then we say that these are increasing in energy because you can think of the electron being attracted to the nucleus. And so to pull the electron away from the nucleus takes energy. It's an attractive force, and you have to add energy. That means that when the electron collapses into a lower energy level, it emits energy. And this is what we see. We see this emission. So what we're seeing is an electron jumping from the 5th energy level down to the 3rd, emitting light. And so we can use the Rydberg equation. The change in energy is equal to the Rydberg constant, which is just a number that you'd be given. Our initial state would be n is equal to 5. 1 divided by 5 squared, minus our final state, 1 is equal to 3 squared, to give us a value. We can plug these into our calculator and use the value of the Rydberg constant, Rydberg constant is 2.18 times 10 to the minus 18th joules, and that's specific for hydrogen. And we get the energy associated with this change. This value is 0.071 negative, which is good. We expect this to be a negative number because we are releasing energy, high energy going to a lower energy state, spitting out that excess energy as light. Change in energy is negative. It's being released to the environment as a photon in this case, a packet of energy. So it gives us a change in energy associated with this photon of 1.55 times 10 to the minus 19th joules. You go, but Dan, this is a really small number. All these other energy values that we're associating with chemical reactions have been really big. Why is this number so small? Well, it's because it deals with one atom. Right? When we deal with changes in reaction energy, we're dealing with millions of atoms or moles of atoms. Right? So this joules would represent the amount of energy released when an electron falls from the 5th energy level to the 3rd energy level for one atom. In terms of moles, this turns out to be something like 10,000 kilojoules. So it's actually a quite substantial amount of energy per mole of material being released. So, but this isn't what the question was asking. It was asking for a wavelength. Now, how do we relate energy to wavelength? Well, luckily for us, we know that delta E is also equal to h nu, frequency, and C is equal to lambda nu, and so we can plug in this value. Delta E is equal to h c over lambda to give us our wavelength in meters. So we take our 1.55 times 10 to the minus 19th joules is equal to Planck's constant. A little creative rearrangement says lambda will be equal to 6.63 times 10 to the negative 34th joules seconds, again Planck's constant, times the speed of light, 3.0 times 10 to the 8th meters per second. All divided by our energy for our photon, 1.55 times 10 to the minus 19th joules. Joules cancel, seconds cancel, leaving us with meters for our wavelength, or 1.28 times 10 to the negative 6th meters. We know that for every 10 to the negative 9th meters, that's equivalent to 1 nanometer. It gives us, in nanometers, about 283 nanometers. In terms of our visible spectrum, that the light wave associated with this n equal 5 to n equal 3 transition would be 1283 nanometers, which puts it actually, this 1283 nanometers puts it in the infrared. So these transitions from various energy levels within hydrogen are actually given names. These are what we call series. And so there's the Lyman series, the Balmer series, the Paschen, named after probably the people that discovered them or went out and found them. And there was our particular transition, 1283, that relates to the transition from the 5 to 3rd. Now, what that means, though, is that if you irradiate the atoms at 1283 nanometers, electrons in the 3rd energy level will hop to the 5th energy level. So you can induce these transitions. At those situations, the energy is absorbed. Right? And so what we see is sometimes, rather than emission lines, we can see absorbance lines. So rather than seeing lines being emitted, we instead see absorption lines, lines that represent dark patches. And so these lines can show up, and this is how they are one of the ways you can identify elements in stars. And so, for instance, here are these dark lines here, here, and I believe here, represent absorptions, particularly for hydrogen in a series of stars. And the stars have different heat classifications, energy level associated with them. And you can see these hydrogen lines showing up very strongly, but yet in some stars the hydrogen line has faded, and you actually see other lines, which actually probably helium is associated with this. Right? So these emission lines are characteristic of elements. So just again, here are some emission lines for a handful of elements, and you can see them showing up. When you start to get to multi-electron atoms, the lines don't show up as pretty. Right? We start to see multiple lines, and you start to see characteristics of lines. And so scientists start to classify the behavior of the lines. So at this point, our model was very simple. These nice, distinct levels, the primary energy level. But in the multi-electron atom, these energy levels started to become not so pretty. Right? We have these lines, and they notice how they're fatter, they're wider. This represents a band of energies, right? Several different lines on top of one another, several different energy regimes. What's going on? As with any science, when your results don't fit your model needs work. And so let's take a deeper look at the multi-electron atom. So our model again is this central atom with these orbits that get higher and higher in energy the farther and farther away you get from the nucleus. Now again, another way of thinking about this is as the nucleus and then these energy levels that slowly increase as you get further and further away from the nucleus. And they start to get compacted at the higher energy levels because they get closer and closer together. So early scientists began to see a pattern, all right? When you looked at the energy levels, each of these shells, the first shell, n is equal to 1, n is equal to 2, n is equal to 3, the calculation started to come out that the number of electrons in each shell was equivalent to 2n squared, the principal quantum number. The first energy level could only hold 2 electrons. The second energy level could only hold 8 electrons. The third energy level could hold 18 electrons, etc. So each of these shells could hold up to that many number of electrons. When you're dealing with the 1 electron atom, it kind of seems stupid. Why do we care about this? But most of our atoms aren't 1 electron. But for the model, they were using these electron regions exist. The atom can hold that many electrons, and so theoretically you could imagine a hydrogen atom with a negative 36 charge, where all these electrons have been dumped into that hydrogen. Right? It's a conceptual model, It's not one that you're going to see very often. What happens? Where are these electrons residing? Clues related to this, the behavior of the multi-electron atom, led to this idea that within each shell, each orbit, the electrons resided in its own distinct environment that we called, well, they were called subshells. You could think of them as within each of these shells, there were multiple sub-energy levels, subshells. The analogy I like is the apartment complex model. Within the first floor, there's only one apartment. On the second floor, there's 2 different apartments. On the third floor, there's 3 different apartments. So within each shell, there are multiple subshells. This would explain the subtle differences in the energy if those subshells had different energies of their own. And so you could jump between the subshells, which would have slightly different energies and therefore slightly different wavelengths of light. Slightly different colors. Right. So these subshells would represent slightly different energies within the primary energy level. So we have the shell model and these subshells.